So, but let's talk about dielectrics. So what we get is that a dielectric is an insulator. That you're going to place in between the plates of a capacitor. One thing it'll do is by putting it in there, it keeps them separate. Because if the two plates touch, then you don't have a capacitor, you have a wire, a really expensive wire at that. And so one reason that they insert a dielectric in between the plates is to physically keep them apart, because they have to be isolated, otherwise the charges rejoin and you really don't have anything. And the other thing is that when you do this, the bottom line is that it will increase the capacitance. So that's what it does. So it's going to increase the capacitance. It also prevents the plates from touching. Because what they used to do is they would take, like a sheet of metal, like aluminum foil or tin foil, and then they would go in and put an insulator like wax paper, and then another sheet of foil, and then another sheet of wax paper, and then they would roll it up into like a jelly roll kind of thing, and then that would prevent the plates from touching one another, and you'd have a very large area, surface area for plate. You would have very close spacings, and so you get a fairly large capacitance that way. Okay. And so the way they write this out is they write down that we have the capacitance with the dielectric. There's usually no subscript on there. And then the book does a funny notation that I have never seen before. Okay. So the standard notation is that they use this little Greek letter called kappa. Now, kappa is a funny letter. It looks kind of like a capital K, but it's really a half-height letter. And so since it looks so much like just a normal K, then I usually go ahead and put a bar across the top and bottom so you know that it's a kappa and not a K. So this is kappa. And so it's a factor times this, initial capacitance. Now, the book just uses K. And so I don't know. I don't know what to say about that, but that's what they do. So, and so this is our, capacitance. With the dielectric, the C with the 0 subscript or the naught is the capacitance without the dielectric. Okay. And then this kappa or K. And see, the thing is I think that in the book they use a K, but then in the homework they use kappas because, yeah, because every other person in the world uses kappa. I don't know what to say. So, so the book definitely has their kind of some unique notational things that they do, which I assume is the author. So. And so this constant is a value that depends upon the material that you used for your dielectric. And so that's going to be in table 18.1 on page 587. Okay. And let's look at our units. So the units of the dielectric constant are capacitance over capacitance. So that's going to be a farad over a farad, which makes this one, unitless. Okay. And the other thing you're going to notice is that since this capacitance is going to increase the capacitance, then our K or kappa is going to be, bigger than 1. So, and that's generally how that goes. So our kappa values, again, depend upon the material that you use. In general, it's, some number bigger than 1. If it is the 1, then that's generally what they treat as a vacuum. And air is very close to that. Okay. And so that's why in our one example, we had an air-filled capacitor, because there was, what they're telling us is that there wasn't any material in between the plates. There was just air. And air has a kappa that's close to 1. So very, very close to 1. Okay. And so that's the basic idea there. And so then what we can do is we can go ahead and kind of look at what's happening in this situation, kind of on an atomic level or on a molecular level, so kind of down in there. And so what we're going to look at is we're going to have our parallel plates, equal amount of opposite charge on the plates. Creates our nice uniform electric field. In between the plates. And so what we're going to look at is that if we have we charged up the plates and then unhooked the battery. So that's the situation we're going to consider. When the charge is constant, and we're, disconnected from the battery kind of things. Okay. Then what we can look at is we can look at that we establish our electric field in this sense. Now, when we go in and we insert the dielectric, okay, now I'm going to envision that we're going to completely fill the space in between the plates. There are ways to handle this if it's not completely filled. So, but we're going to picture that it completely fills. Okay. And so what happens is it depends upon the material that the dielectric is made out of. Okay. So for a polar dielectric, okay, then what we get is you have, equal amounts of opposite charge, separated by some distance, creating an electric dipole. And then when we place this into an electric field, a uniform electric field, like so, then what you're going to get is there's going to be a force on the positive end that goes in the same direction as the field, and then an equal but opposite force on the negative end of that polar molecule or atom, whatever, that goes in the opposite direction. Okay. And so what that's going to do is it's going to cause it to torque. And essentially it's going to rotate until it realigns in our electric field. So this is this initial electric field, and we'll label this as the EO to begin with, right? And so then what's going to happen is it's going to create that while there's no net force, the molecule will not accelerate, but it will exhibit a torque. And if possible, especially if it's like water or something that can move, then it's going to rotate itself until it aligns like this, okay? Again, we have equal and opposite forces, so then the net force is 0. It's going to rotate it like so. Okay. Cause this to rotate until it lines up like this. And then what you get is that you have an electric field from the dipole. And notice that it runs in the opposite direction of the electric field that we placed it into. So then the overall effect is it's going to basically work to cancel it out, or, well, reduce it. It would never really cancel, but it's going to reduce the values, okay? And so this is for some sort of polar material, okay? I said water is a good example of that kind of things. And if we have a non-polar dielectric, okay, then what we get is that initially we would have our center of the positive charge is somehow surrounded by our negative charge. And so then the center of the negative charge and the center of the positive charge coincide. Okay. They're at the same place. But then if you put them into our electric field, then what happens is that it's going to deform the orbit of the electron, so that it's going to orbit, further over. So here's the nucleus, the center of the positive charge. And then what happens is that the electron orbits further down so that it basically induces a separation between the center of the negative charge and the center of the positive charge. So it induces a polarization on that, atom or molecule. And these are equal and opposites. And so then what that'll do is that'll create some small electric field from the dipole that goes in the opposite direction of the field that you put it into. This is supposed to be a non. And so then the idea here is we can look at our net electric field. The net electric field is the electric field without the dielectric added to the electric field contributions from the dielectric that all go in the essentially the opposite directions. And so what you end up with is it all ends up with, these little, drawing some representative ones. So then my E from the dielectric, they go like this. Once everything's lined up. It's in the opposite direction of the E to begin with. And so then if we look at magnitudes, then that's this initial magnitude minus the magnitude of one from the little dielectrics. And so then this means that it's now smaller. So we've reduced the overall electric field. And the way we can calculate that is we can calculate that that's the initial magnitude of the electric field divided by our dielectric constant gives us the magnitude of the electric field, with all those little cancellations that occur. Okay. So the overall effect is that we would reduce the electric field in between the plates because it's being essentially, canceled off by the field from the, either the polar molecules or the induced polarization on the atoms or molecules within the material that you put in between the plates. Okay. And so then what this tells us is that we can note that since our plate spacing remains the same and our magnitude of the electric field is the potential difference over the plate spacing. And by sticking the dielectric in, we've dropped the field strength. Since this one goes down, but the spacing stays the same, then that one goes down. So then the potential between the plates drops by inserting the dielectric. And so then the implication here is it goes down by the same factor. So then the potential with the dielectric is that initial potential between the plates divided by our kappa kind of amount. And so so the dielectric will increase the capacitance but it decreases the magnitude of the electric field and the electric potential. As long as our Q is constant. There's the other case where it's not, but I don't care so much about that. I just want you to get the basic idea of kind of how things work. And so then we can see that our, Q is equal to C times that voltage. And so this is what you see here is that this is going to remain constant. And that when we stuck in the dielectric, then the capacitance goes up. And so therefore that potential has to go down to maintain a constant Q in that instance. Okay. And so I think this is a useful thing to be able to kind of picture in terms of what's happening on this particular